Hello, welcome to Unit 11, Day 8's video. I'm going to start with the warm-up, but hopefully you've all been handed out this worksheet. Just make sure it's off to the side. We'll come to that in a second. That's where our notes are going to be. But if you have your warm-up log, maybe take that out and jot these notes down, because this is going to kind of review the kinds of formulas we've done for the last couple days and also get us to a point where we're ready to hear about what today's stuff is. So, Part A says, suppose that $1,000 is invested in an account that grows at an annual rate of 8%. If no withdrawals are made, find the amount in the account after 10 years. Okay, so there's no words like compounded or anything like that in here. So if it's just growing by a constant percentage rate, then we're using the formula A equals P times 1 plus or minus R to the T. So this is obviously initial amount of 1,000. So we'd have A equals 1,000 times 1 plus, because it's growing at an annual rate of 0.08 raised to the T, which is 10. So we can clean that up a little bit if you want. Make it 1,000 times 1.08 to the 10th. And let me grab my calculator here, and we're just going to type that all in. 1,000 times 1.08 raised to the 10th gives us the nearest cents, 21.58 and 92 cents. Okay, so that was the kind of the easy exponential formula that we use, and that's when there's no words like compounding. It's just constant annual percentage rate. Now, the last couple days we've been going over questions like this. What is the monthly interest rate of this account rounded to the nearest tenth of a percent? Write a formula for the amount in the account after T years in terms of the monthly rate. So this formula describes everything in terms of a yearly rate. So if I want to know what the monthly rate is, what would T be? Remember, T is in years, so 1 month in years would be 1/12 of a year. So I would take A equals 1,000 times 1.08 to the 1/12. And remember, the 1,000 is not affecting the rate. It's this part in here where the rate is kind of contained. So that's when I come over here and I figure out what that is first. So 1.08 raised to the 1/12th power is 1.00643 blah blah blah. So 1.00643 dot dot dot, and that's equal to that 1 plus R, because that's where the rate's contained. So if I want the rate, the R value is 0.00643. That's R. It says round to the nearest tenth of a percent. Well, remember, if I want it as a percent, I got to move the decimal place 2 places to the right. The nearest tenth of a percent would be 0.6%. So that's what R is. R is about equal to 0.6%. That's the monthly rate. So now if I want a formula in terms of the monthly rate, it would be A equals, still the same initial, 1,000. 0.6% would be 1.006. Instead of just raised to the T, that's a monthly rate, and T is in years, so it'd have to be 12T. So if I put 1 year in here, it'd be 12 of these monthly rates. If I put 2 years, it'd be 24 of these monthly rates. So that's my answer. Okay, and then finally, this is going to be the last type of formula we've done so far. If the annual 8% rate is compounded monthly, what is the amount in the account after 10 years? So anytime you've got compounding involved, you should be thinking of A equals P times 1 plus R over N raised to the NT. And remember, that means where N is the number of compoundings per year. So if we're compounding monthly, what's N? N is 12. So I'd have A equals 1,000 times 1 plus that original 8%, so 0.08 over 12 raised to the 12 times 10, or 120. Type that all in. 1,000 times 1 plus parentheses 0.08 over 12 parentheses raised to the parentheses 12 times 10 gives you 22.19 and 64 cents. Okay, now remember, when you compare these two answers, the first one and this one, they're similar, but this one's slightly better because compounding more frequently, remember, gradually gets us more money. But we talked a couple days ago about what about if we compounded yearly versus monthly versus daily versus hourly versus minutely versus infinitely. You can't plug in infinity for n, so how would you do that? What's the limit? What's the most you can earn no matter how many times you compound? Well, that's what we're going to talk about today. There's your random fact. Ketchup was once sold as a medication. Okay, switch over to your notes. Okay, so this first part might sound a little random, but it is connected to what I was just talking about in the warm-up. It says, what is the valued expression 1 plus 1 over n to the n power as n gets larger and larger, or as n goes to infinity? Now, it might be a little hard to see, but this is actually part of a equals p times 1 plus r over n to the nt. It's essentially that formula. If I make p equal to 1, r equal to 1, or t equals 1, the only thing I'm leaving is this n value. So basically I'm asking what happens to the number of compoundings, which is n, as the number of compoundings goes to infinity, what is that effect on this whole equation? So what I did, and you don't have to do this, but I went to my calculator, I put in that expression into y1, I made sure my table was on ask, and then I plugged all these values in. And this is how we look at limits. This is kind of a calculus topic, actually. But these are the values as n gets larger and larger. So as n is approaching infinity, what's happening to these y values? And you can see them right down the list here. We've got, I'm just going to fill them in on the sheet for you. We've got 2.5937, and then we've got 2.7048, 2.7169, 2.7181, 2.7183. This also says 2.7183, but it's just the decimals are changing so far down out of the range of the calculator that you can't see it. So it says, do the values in the table appear to be approaching a fixed decimal number? What is that number rounded to 3 decimal places? So they're getting closer and closer and closer to a certain value. It's kind of reaching a certain limiting value, which you've heard of as an asymptote. So that's, as n behavior as n goes to infinity, is kind of like talking about what asymptote is it approaching. And it's approximately equal to 2.718. And the conclusion that I want you to draw from that is, as number of compoundings approaches infinity, we are approaching a fixed decimal constant. I'm just going to say a fixed constant. And that constant is called the number e. So e is a number kind of like pi. It's irrational. Pi is 3.14159265338, blah, 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 blah. E is similar to that, 2.718, blah, 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 blah. So that's what you want to think of it as. It's kind of like a number like pi, and this is called continuous growth and decay. So here's this definition. The number e is a mathematical constant similar to pi that is used to model growth and decay, that is changing continuously. And that's a key word that I'm going to keep mentioning today. Whenever you see that word, continuously or continually, probably E is going to be involved. And it's sometimes referred to as natural growth and decay. A lot of processes in nature follow this pattern, so that's why it's called natural growth and decay. And e is about equal to 2.718, just like pi is about equal to 3.14. Okay, so I want to evaluate these numbers just so you get used to where they are in your calculator. So the e button, you can see next to the 4 here, it says e to the x. That's one option. If you click that button, it automatically gives you an exponent, because these are mostly used with exponents. If you don't want the exponent option, if you look at the division key, there's also an e on that one. So if I want to just figure out what e is, I can go to second division, hit enter. There's that 2.718 number. Oops. Sorry. Okay, so anyway, that e number I can plug in as 2.718. And all these other ones are just similar decimals, so I can do like e, oops, I can do e raised to the negative first, that's 0.3679. If you'd rather use that exponent e button, e squared, 7.389. E to the 10th. It's going to grow pretty quickly. 22,026. 0.47. And then e to the 100th. Huge number. It's like 2.69 times 10 to the 43rd. So just know for all these in calculator, where you know that button is, it's either second division or second ln, whichever button you'd rather use. Okay, now let's also talk about what the graph of e to the x looks like. We're going to do some transformations with it in a second. So this is our parent function. Is e to the x. And notice the base is e. Do you think this is going to be an increasing graph or a decreasing graph? Well, remember, e is 2.71, so the base is bigger than 1. So increasing. And if you remember back from early on in this unit, every exponential parent function had what as its y-intercept? They all had 0, 1. And this is no different because e to the 0 would still be 1. They had what as its asymptote? They all had y equals 0. So this also has y equals 0 as its asymptote. We also always talked about those accuracy points, remember? That's what I get when I plug 1 into the parent. So if I plug 1 in here, what's e to the first? Well, it's 2.718. So it's 1 comma e, or approximately 1 comma 2.718. So somewhere right about there. That's what your graph would look like. And obviously your calculator can confirm that for you also. You go to y equals, type in e to the x, and zoom standard, and you'll see that same exact graph. Okay, so this is a little bit of review from earlier in the unit. Let's try on the next page to do some transformations of e. So here we go. First I've got y equals 2e to the negative x. So clearly, what's our parent function? Remember, the parent function is always base raised to the x. So this would be y equals e to the x. And when we got to talk transformations, we always want to talk about what's different from the parent and this original function. Well, there's a negative up here, and there's a 2 here. Which of those would have to happen first? And this is where some of you struggled in the past. You got to think PEMDAS. 2 is being multiplied, but this negative is in the exponent. That happens before multiplication. So step 1, what's that negative with the x do? It's a reflect. Reflect in which axis? In the y-axis. And what does that affect? We negate the x's. And then I've got that number out front, that 2. What's that doing? That is a vertical dilation by 2. And that means we multiply all of our y values by 2. Okay, so if I use my parent function, I started with y-intercept of 0, 1. Once I negate the x and multiply the y's by 2, negative 0 is still 0. 1 times 2 is 2. So now this is my new point. I started with a asymptote of y equals 0. And when I negate x, that doesn't affect it. And 0 times 2 is still 0. So I've still got y equals 0. And my accuracy point, which was 1e, negate the x, becomes negative 1. Multiply y by 2. So now it's 2e. Let's see what that would be. So if I type in 2e, we get about 5.4. So negative 1, 5.4. 1, 2, 3, 4, 5. Stay right about there. Connect those dots, and you've got your graph. As another review, what's the domain of this graph? Negative infinity to infinity. And what's the range? Lowest it goes is 0, not included, goes up forever. Okay, one other one over here. We've got g of x equals e to the x plus 2 minus 3. Try to section this off here for us. So again, what's our parent function? Parent function is always y equals, and it's the base, which is e to the x. Talk about transformations. What does this function have that our parent does not? We've got a plus 2 up here, a minus 3 there. Which of those has to happen first? Since the plus 2 is in the exponent, that has to be the first thing. And what does that do? So translate left 2 affects the x's, x minus 2. And then that minus 3 is a translate down 3. So translate down 3. And what does that affect? That's the y's, so it's y minus 3. To get our critical values, we've got our original intercept of 0, 1. When I subtract 2 from the x's, it becomes negative 2. Subtract 3 from 1, I also get negative 2. So negative 2, negative 2. Original asymptote of y equals 0. Subtracting 2 from x doesn't affect that. Subtracting y by 3 does. Becomes y equals negative 3. There you go. And then accuracy point, it starts as 1e. Subtract 2 from the x's, now it's negative 1. Subtract 3 from the y's, so now it's e minus 3. And let's see what that is using our calculator here. So e minus 3 is about negative 0.28. So negative 1 and negative 0.28 would be right about there. So connecting those two dots gives us that graph. And what's the domain of this graph? As every exponential function, negative infinity to infinity, no one should miss that on the test. The range is dictated by the asymptote. The lowest it goes is negative 3, but not including it, and it goes up to infinity forever. Okay, so that's how you do transformations with e to the x. Hopefully that was a good review of transformations for you. If you're still having trouble with those, try to get help for the test that's coming up in a couple days. Okay, last thing, we've got some application questions. How are we doing on time? Looking good. Okay, modeling natural exponential growth and decay. Continuously compounded interest. Continuously, again, there's that key word. Continuously compounded interest is modeled by this equation. A equals P e to the RT, PERT. Now look at how that's related to what we already know. The formula for compounding in the past has been P times 1 plus R over N raised to the NT. From what I showed you at the beginning of the day, this piece, if I plugged in infinity for n, or if I could look at what happens to that as n goes to infinity, that's this right here. It becomes e. So it's like I'm plugging infinity in for n here as n goes to infinity, what we saw on the last page here. I hold everything else constant and just make those compoundings go to infinity. I'm approaching e. So that's why the formula has e in it. The rate's still there, the initial's still there, the time's still there, but n has been taken out for that e value. So, example 1. Suppose that $1,000 is invested at an annual rate of 8% compounded continuously. Find the total amount in the account after 10 years if no withdrawals are made. Okay, so I'm going to make another note again. Note. Continuously means per. Make sure you use PERT. Okay, so for part A, we know we're using A equals P E to the RT. So I want the amount in the account. So I'm going to be looking for A. So our initial amount is 1,000 times E. The rate is 0.08 and T is 10. We can just plug that in one step if we're careful. So 1,000 times E, it's going to raise to the 0.08. And you got to type times 10. And that's the correct answer, 22.25 and 54 cents. Look at what happens if I do this. A common mistake is to write 1,000 E to the 0.08 times 10, like that. Totally different answer. And that's because the calculator is raising it to this 0.08 and then multiplying by 10. You need to write it like this first way that I did so that it all stays in the exponent. So everyone make sure you're looking up here and understand that. Got to stay in the exponent. Okay? So coming back to this here then, this is equal to 2225 or 2,225 and 54 cents. Part B. How long to the nearest tenth of a year before the account grows to $3,000? Okay, so now this is when I'm plugging in 3,000 for A. I'm looking for what variable? Well, I know the rate still is 0.08, so it's T is what I'm looking for. And the only way we know how to solve this is graphically. This is Y1, this is Y2. So we go to our calculators one more time here. Go to Y equals. In Y1 I'm going to put in 3,000. And in Y2 I'm going to put in 1,000 times E raised to the 0.08x. Remember, I always want you to go zoom standard first, but we're going to see nothing because I'm looking for 3,000. I'm only going negative 10 to 10 right now. So I need to change my window. What do I want to change in my window? Ymax for sure. So go down to Ymax. Since I want to see 3,000, let's make it 6,000. So there's the 3,000 line. I want to just see where these connect. Hopefully I'll see it. Oh, not quite. So I got to change my Xmax also. Don't have to go too far because I almost saw it. So let's try 20. There's 3,000 again. And this time I see it creeping up. There it connects. There you go, second calc intersect. First curve, second curve, guess. And it looks like it's going to be T is 13.7 years. So I remember what I need to see. I need to see a graph. We did negative 10 to 20 and negative 10 to 6,000. It looked like this. And we got the T to the nearest tenth was about equal to 13.7 years. Hopefully that made sense. Hopefully no questions. If you had calculator problems, ask your person or your neighbor next to you. And here's the last one. In a state park, the deer population was estimated to be 2,000 and decreasing continuously at a rate of 4% per year. If the decrease continues at that rate, what is the expected deer population in 10 years? Okay, what's it say? It's decreasing continuously. Continuously means what? PERT. But again, it also says something else here. It says decreasing. How's that going to factor in? Well, that's just going to mean that your R values is negative. Okay, so part A. We want the expected population. So I'm using PERT. I'm solving for A. So A is equal to the initial population, which is 2,000. E to the, now instead of 0.04, it's negative 0.04 because the deer population is decreasing times T. And oops, actually we know what T is too because we want it in 10 years. So let's just say negative 0.04 times 10. So I should be able to type that all in. 2,000 times E raised to the negative 0.04 times 10. And it looks like about 1,341 deer. And then for part B, in how many years to the nearest tenth will the deer population be half of its current population? So in how many years? That means I'm solving for T. What's half of its current population? Its current population is 1,000 or 2,000, so half of that's going to be 1,000. So I'll have 1,000 equals 2,000 times E to the negative 0.04 T. If I'm solving for time, I can't solve that algebraically yet. You will in a couple weeks. But I can do y1, y2. So back to my calculator one more time. This time y1 is going to be 1,000 and y2 is going to be 2,000 times E raised to the negative 0.04 x. Assume standard. That resets the window. We're not going to see anything right now, so I'm going to have to change it. We know first to make y max at least 1,000. It's a good idea to make it 2,000. Then hit graph. See if we can see where they connect. And not quite yet, so we got to go to the window again. This time change what I need to change to go this way. X max. Let's go 50. Looked like it wasn't quite there yet. So it's kind of just a guess. There I can definitely see it. And second calc, intersect, first curve, second curve, guess. 17.3 because it said nearest tenth. So don't just write that, show me your graph. So 17.3 years. And we had negative 10 to 50, I believe, and negative 10 to 2,000. Okay, so that's all the lesson for today. You should have a worksheet for homework. Do the best you can with that. Remember, continuously means E. This is what your homework looks like. Now, be careful. Some places in here, we're not talking about E. Like you see this first one, Kyle is ready for college because it's compounded quarterly. That's that one of those older formulas with the ends in it. This is compounded continuously, so now I'm using PERT. If I'm decreasing at an annual rate, then it's just that 1 plus R formula. So it's all kind of mixed together. So make sure you're watching when it's E and when it's not E. And then there's a transformation question also. Check your answer key, do your best you can with it. I'll be around tomorrow in the morning and throughout the day if you got any questions. Good luck.